welcome back everybody. This is the second video in the design and architecture module for Software Engineering 1, and today we're going to talk about an architectural case study that kind of makes all the stuff that we talked about last time kind of concrete. So last time we talked a lot about the design workflow and sort of all the questions that come out of the design workflow, what the intent of the design workflow is, and really it's all around trying to take the software specification that you create during systems analysis and change that into a technical specification that an engineer or an engineering team can actually take and then go away and start implementing code. So we also talked about architectural debt, which essentially happens when your technical specification itself has defects in it. And so if you've chosen the wrong type of application to build, you're obviously going to have some defects in your specification. If you have chosen the incorrect way to split up the application, then you're obviously going to have some defects in it. And so we talked about how architectural debt is kind of a subset of technical debt. And it has some dire consequences if you have too much architectural debt during a project. And so today what we're going to do is we're going to go into a concrete kind of example of a system and talk about the design considerations for trying to build out that system and how their answers, sort of the answers to the design questions, can impact the amount of architectural debt that you have in the project. So the whole rest of the lecture is going to be based on one central problem, and the problem looks something like this. So let's suppose that we have a property and casualty insurance company, and that insurance company is asking you for a system that does these three kind of high-level things. First, they need to track which of their clients has an active policy. Second, they need to track premium payments to understand who is actually currently paying for their policy. And three, they need to generate sales reports to give to agents so that agents can go out and renew policies, sell new policies, or get people that have existing policies that are not paying to come back and actually pay and make their policy current. So as you may see, you can get sort of client requests, and that's effectively what this is a client request. This is certainly not an exhaustive list of functional and non-functional requirements. If you just have a client request, you might have drastically reduced ability to actually perform system analysis or design. So if you don't know what a property and casualty insurance company is, you're probably going to miss some fairly key parts of what the system is supposed to be doing. And so moreover, if you don't understand anything about the specific company that's asking you questions, you might not even know how they're trying to use the system. And so from this problem statement or this client request, it doesn't tell us if their sales agents are remote or if they're working in a call center or if they are going door to door, for example. And so that context that the people are working in is going to change your answer to some of these design questions. And basically, design itself is predicated on the idea that not all of the design decisions that you can answer and all the designs that result from your answers to these questions will have the same amount of technical debt, and they won't have the same amount of architectural debt. And so as a software architect or a member of a software team, what your goal is to design a system that sort of leaves the gate, the starting gate, with the least amount of architectural debt as possible and on a path to accumulate the least amount of technical debt possible. So if in the future you find yourself working on a project and the specification that you are working from looks something like this, you should maybe pump the brakes and go back to the requirements gathering phase or back to the systems analysis phase. If you're trying to build a system solely off of these three bullet points, it is almost impossible that your idea of what the system should do and the client's idea of what the system should do will be the same. So there's a huge room for error there, and that's a huge risk to the project. So what you should do is you should at least take those 3 bullet points and kind of iterate over them, and iteratively figure out what are all the functional requirements, what are all the non-functional requirements, and build as close to a sort of rigorous or a formal specifications document as you can, so that you can intelligently answer these kind of design questions. If you're trying to answer design questions from something closer to a client request in a specifications document, you also kind of have to live with the fact that you're going to expose yourself and your company to a lot of risk. And if both sides are okay with that risk, then that's kind of okay. But you can certainly, you will see throughout the lecture the benefits of going through the first couple of steps that we've talked about in previous weeks. So just with a rudimentary understanding of what PNC insurance is and kind of the 3 basic bullet points that they gave to us, we can identify some kind of high-level concepts, some basics that we can use to perform some object-oriented analysis in this case. And so we see that there are probably going to be 2 user classes because we're going to need to support salespeople, but we're also going to be able need to support people who actually make organizational decisions about the company. And so we're going to call that latter group staff accountants. And so staff accountants are going to be responsible for understanding the amount of revenue that's supposed to be coming in the next month or the next quarter or the next year. And that's different from sales agents who are supposed to be going out and sort of selling new insurance or renewing policies and that kind of thing. So out of the gate, from an analysis perspective, we know that we need a user class or something like it that allows people to have different roles. But within those different roles, their actions or their activities are largely the same, right? They're going to want to be able to log in. They're going to want to see policy information, see payment information, and sort of track the same kind of data. The difference is the way that data should be displayed. And so salespeople probably are most interested in accounts that are held by people that they have the best relationships with. So if you have a best friend that isn't current on his policy, it's much more likely that you could go and talk to your best friend about paying his premium than some rank stranger. The accountants are probably going to be more interested in who owes them the most money. So it doesn't really matter who they're friends with. What matters the most is that they have $1 million policy that isn't being paid on versus a $200 policy or some crazy thing that isn't being paid on. So obviously you might not have a whole lot of exposure to what PNC insurance even is. So property and casualty insurance is automobile insurance. There's several other types like workers' comp and all that, but here what we're talking about is automobile insurance that covers things like vehicle accidents. And so obviously when you have a vehicle accident, it's very often that somebody ends up going to the hospital or getting some sort of medical care. And usually hospital records are used to determine how much money the insurance company is going to end up having to pay out to cover your claim. So basically how this works is you pay your premium and you pay that every month, and then when you have a car accident during a covered month where you've paid your premium, the insurance company will pay whatever their insurance contract or your policy dictates that they should pay. And so hospital records are used to understand what the expenses on the part of the insurance company will be. And so they need these hospital records in order to do their job. But hospital records themselves are protected by HIPAA. So if we build a PNC application that has very weak security, what can typically happen is somebody can gain access to HIPAA protected information like the length of your hospital stay or diagnostic information. And that is a data breach that could result in criminal penalties, certainly civil penalties, and it could be a severe black eye for your company, and it's basically just all around bad. So this is a core example of something that you might just accidentally stumble into unless you do a fairly rigorous sort of requirements gathering process where you talk to the client and the client is capable of kind of telling you all of the requirements, not only from the system perspective, but also from the legal perspective for the system that they're trying to get you to build. So in the process of iterative requirements gathering, you could find out things about how the users actually utilize the system. And so in this case, for example, you might find out that the users are actually sharing all of this data with a single data file. So they're using something like Microsoft Access, for example, that has effectively a glorified spreadsheet, and people share the spreadsheet around every other day of the week or something like that, and they load the spreadsheet with Access or with some homegrown system. And what that means is that the file itself is unencrypted. It's basically just an Excel file that they're going around sharing, and they're potentially sharing that through an insecure and unsecured channel. And so in this case, you can already identify that the company is not in compliance and they have a lot of risk associated with being sued if somebody gained access to data that they were not supposed to have access to. So we're going to talk a little bit later in the semester about how to kind of position software projects and products and software organization. This is a very sort of important cornerstone of that. If you can identify through the analysis process core missing functionality of competing software or previous systems, you can always sort of add value in that area to your product and then gain more users that way. So we talked about four primary sort of architectural styles that we'll talk about in this course. There are dozens and dozens and dozens of these things, as I've said numerous times in the course already. Basically everything in software engineering is on a continuum. What we're doing is we're looking at four very sort of concrete snapshots of that continuum. So what we're going to do is go through a thought experiment on each of those four types, and then we're going to talk about the pros and cons of each, and then which one should probably be used in this case. So if we are to make a desktop application that's going to sort of implement this PNC system, what's going to happen is you're going to have staff accountants. They're going to be in their offices, and they're going to be kind of okay. They're going to have desktop computers with really big monitors. They're going to be happy to do their work on a desktop application. It's not unlike people who are using Word sort of every day. The sales agents, however, probably not going to be happy about it. And fundamentally, they're not going to be happy if they have to carry a laptop around to remote meetings, for example. So if they're sort of going door to door, or if they're meeting clients in their houses, they don't necessarily want to have to take a laptop. They would much rather use a tablet or a mobile device. And we also talked last time about how current technology and current sort of architectural trends are moving away from thick client applications. And so not only are you going to have this issue where the sales agents, users are going to be angry about the system, you're also going to go ahead and start a project kind of behind the eight ball. You're going to start a project that you already know has a significant amount of obsolescence baked into it, and that isn't necessarily where you want to be. So desktop application doesn't really seem to be the best scenario right here. So you would usually just sort of mark this off your list, and you would go down the list to the next one. And so next we could talk about what happens if we make it a mobile app. So if we make this thing into a mobile app, sales agents themselves are going to be super happy. Because even if they have to go to meetings at client houses, they can do all of their work from their cell phone. They don't actually really care, even their iPad or something like that. So it's going to be an ideal situation for the sales agent. It's not going to be an ideal situation for the accountant, though, because now they have these very nice monitors on their great desktop in their nice quiet office. But instead of using their desktop machine and their fancy monitors, they're staring at their phone with their head in their lap in their desk chair, which is not necessarily great. In addition, mobile applications typically struggle with security, and that is because you can secure your app, but you can't necessarily secure the phone. So you can do something like require the user to log in every time they launch the app, but typically what will happen is users will get agitated by that, and so the users will always say, well, I stopped using the application because I have to log in every time, so I log in once a day or something like that. And if you don't do that, what can happen is the user could have no PIN on their mobile app. They could lose the mobile application, and then suddenly you have HIPAA protected data in the hands of who knows who. And so you could become liable for a data breach that you had nothing to do with. And it's not necessarily a great situation. And so for that reason as well, maybe mobile app isn't maybe the best way to do things. And so a mobile application is certainly closer. It checks a lot of boxes in terms of the sales agent. The accountants would be kind of mad just because of the UI. It would certainly be better in terms of architectural debt, but it's still not ideal because of these two things. A, the accountant can't use the hardware that they already have, and you have this security issue that isn't necessarily easy to fix. And so that's not necessarily ideal. We would go to the next one. So the next one would be a web application. So what would happen if instead of a mobile app, we make a web app? And so the accountants themselves, they could sit in their office on their nice new desktop, and they could go to a web browser, and they could actually work on the web app from there. Likewise, agents could access the web browser on their phone or on their tablet or on whatever, and they would have largely the same experience. So maybe the application looks slightly different based on the size of the screen, but all in all, it would be a pretty good trade-off. And so this is what I would refer to as a sort of Goldilocks situation. If you're trying to build a game, maybe this is not the best situation, and maybe the best situation would be a mobile device, a mobile app. In this case, like data management kind of stuff, web applications typically serve the best purpose. So what we found is that this web application is going to solve a lot of the problems that we have. So it's going to solve the security issue because you can use sort of all the standard kind of browser protection that has been used for decades at this point. It's going to fix the situation where you have two different types of users that are doing different jobs, needing to see different screens via the same application. But given the kind of rudimentary understanding of what the system is supposed to do that we currently have, we have a lot of questions. So the first of these is what should happen when a user logs into the system? So should the screens all be different based on the size of the screen? The answer is probably yes, because you're probably going to have people on mobile devices versus people on their desktop, and you're probably going to want to optimize the experience for each of those screen sizes. But even more than that, should the user see different things based on their job functions? So should a sales agent see different things than a staff accountant? Typically the answer to that would be yes. And so you have to understand what those designs should be. And that becomes sort of the bridge between systems analysis and design. During the analysis phase, you would understand how their current process works. In design, if there's a functional requirement that the user should see different things, you should design both of those views to optimize the experience based on the user's role. You also have kind of fundamental questions around data. So if you're using a web application, you obviously don't want to store the data locally on whoever's machine, because you want to be able to share data in a secure way. And that's one of the benefits of doing a web application to begin with. So do you want to store that data on premises? Do you want to store that data in the cloud? This becomes the sort of core buy versus borrow, on-premise versus cloud kind of question. And then the last one is, if you're going to buy all in to a web application, what happens if you don't have internet? So it kind of makes sense that the user would be able to use their mobile device. What if they're using a tablet that doesn't have cellular data? Do you need to support offline capabilities so that you can use the application without direct access to the internet? This is a common question to ask in scenarios like this. So last time we talked a little bit about services-oriented architecture, or SOA, and we talked a little bit about how it has kind of grown up, and we talked about REST as a form of architectural debt if you didn't necessarily jump on the REST bandwagon right out of the gate. And so what I want to talk about here is kind of how services-oriented architecture works from the perspective of a web application. And so we've talked about how of the three kind of architectural styles that we've been talking about, the web application kind of fits this problem statement the best. And so services-oriented architecture gives you a very easy way of dealing with a complicated web app, and so that's what this diagram is supposed to show. So on the right-hand side of this, we have the user that's actually using the application via a browser on their machine. And on the far left, we have database and persistence components. And so these are claims, and these are policies, and these are payments from maybe 10 or 15 or 20 years ago, and also from 15 minutes ago. And we're trying to get data from this database to this user and input from this user to this database kind of seamlessly. And so the browser acts as the UI component. This sort of gives you all the controls, and gives you all the client-side kind of business logic. And you have some form of hosted web service that can take information from the user and translate it into database records, and can take database records and then translate them into something that the user can see and kind of touch and actually work with. So in one case, we have the user kind of sending data down to the database. In the other case, we have the database sending information back to the user for interaction. This whole thing is called services-oriented architecture, or multi-tiered application development. And it's usually described in 4 tiers, but you can see this broken down into many different tiers. And I'm just going to talk about kind of the base case. So in the base case, we have data entry, which happens through the browser. So this is text boxes and drop-down boxes and search boxes and buttons and all that kind of stuff that's taking information from the user and then pushing that information down into a web service. You have data validation that can happen either on the client side, so things like this is a required field, or it can happen on the service or the server side. Things like this is a payment for a policy that's already paid in full, and so you wouldn't want to apply more payment than should be paid on a policy. So data validation can span across machines. It can even go all the way down into database and persistence. Data validation is basically making sure that the data that's in the database makes sense and that it's clean. Business logic is often on the server side in service-oriented architecture. This is kind of the ideal purist kind of way of thinking. The idea is you want to minimize business logic on the browser side, because any business logic you put in the browser is going to make the website slower to react. And so you might have some here in terms of caching and stuff like that, but most of the business logic will be handled in the actual web services, so that the application in the browser itself doesn't take up very much space, and it doesn't kind of bog things down on the client's machine. And then persistence is basically just a database, right? It's a relational database, it's a NoSQL database, it's a file system somewhere that has a bunch of files that your proprietary services can read. And so this is basically deep storage in terms of the overall application. So we talked a little bit about the sort of progression of services architectures in the last video. What I want to do here is kind of go a little bit more into detail about that. And so the first kind of older case is called SOAP, which stands for Simple Object Access Protocol. And this is entirely based on XML. And so in a couple of words to describe SOAP, it's older, it's bigger, and it's harder to maintain. And it's harder to maintain largely because A, it's stateful, and B, it's bigger. XML compared to JSON is very large, it's very verbose, and so it takes a lot more resources to actually transfer information in that format. So REST stands for Representational State Transfer, and it is stateless. So basically what happens is you have entities. So these entities are classes, and they have all of the information that you need for a specific database record or a persistent component. And then your services operate on those classes. And so you can think about it from an object-oriented perspective as data members exist on the entity, and then the sort of business logic or the methods or the function members exist on the service. And so the service takes in an entity, does some work on it, and then passes it off to persistence or back to the user, and doesn't maintain the state of that entity. It is completely unaware if you call it the third time that you have ever called it before, or the information you passed to it the first time that you called it. So in general, REST is a newer way of doing things. It's much smaller because it does not use XML. It actually uses JSON most of the time, and it is easier to maintain in general. So after we've done our first set of thought experiments about what kind of application are we actually even going to build, now we get into the sort of second tier of thought experiments, which are how are we going to answer these questions? How are we actually going to implement our web application? So what happens if we use SOAP services for the design? Well, part of SOAP is using verbose XML packages to transfer state from the user on the right-hand side of our previous diagram all the way down to persistence on the left-hand side. And so how does the answer SOAP interact with the users of the system, and how does it interact with the architectural debt that we're taking on? So accountants themselves are probably totally fine because they have high-speed internet. They're in their offices, they have T1 or they have some crazy fast internet, and the fact that they are having to ship lots of verbose packages of information back and forth doesn't really impact them all that much. Agents are probably maybe kind of okay as long as they stay in areas where they can have access to high-speed internet, or if they have 4G or something like that. It's going to be laggy, but it's not going to be impossible to work with. So if we go back to our kind of simplified diagram and think about what this diagram is going to look like with SOAP, a user is going to want to maybe process a payment. So they're sitting in a meeting with a person. That person gives them a check, and so they want to allocate that check against the policy so that if the person gets in a car wreck after the meeting, their policy will be considered paid. And so they're going to take this policy XML document. They're going to potentially take another payment XML document and the client XML document, and they're going to send that stuff over to the database persistence module. These documents are going to tell the hosted web services what to update in the database. That persistence is going to happen, so you're going to have a new payment record in the payment table. You're going to have an update to the client table that says this client is paid in full. You're going to have an update to the policy table that tells you the policy is in force, so on and so forth. And then the database layer is going to send the all clear back to the user. And so it kind of completes the circuit. It's going to say, yep, I got all of your documents and I made the database updates, everybody's happy. If I'm working with 5G or Wi-Fi, everything's probably going to be fine. I'm not going to have any problems. If I'm using 2G or LTE or some like less than superstellar connectivity, I'm probably going to get down to the web services, and then I'm just going to wait for a while, and I'm not going to necessarily know what's happening. It's just going to be kind of spinning on my application. And then suddenly I could get some weird error, and you don't actually know what happened. Is the database updated, or is the database not updated? Do I need to resend the payment? Or if I resend the payment, is that going to be double paying? And actually, in the spring, I ran into an issue with an application, with a web application that was using something very similar to SOAP. That is used to pay my mortgage. And so actually I was in the situation where I tried to pay my mortgage and it got to this point and then it failed. And then the bank was actually unable to tell me if the payment was applied or not for 5 days, and I only had 1 day to make the payment. So these are kinds of things that happen all over the place, and it's kind of sad. And you definitely want to try to stay away from this kind of user experience if at all possible. So as we talked about last time, the best software architects are pessimists. They assume that everything is going to go wrong at every turn you possibly take. And what you want to do is you want to make sure that even in these worst case scenarios where you only partially get the message down to the services layer, that you get user feedback and that user at least is aware of what is happening, so you don't just get some garbled error back that they don't really know what to do with. These people are currently, if you remember our kind of problem statement, they're currently sending this huge data file over email. And so it's very unlikely that they're looking for a kind of instant feedback. But if you can give them instant feedback with the new system, why wouldn't you? And so even in the case where it's kind of okay if you drop some packets and you have to redo some work, this client may not care because it's still better than what they've currently got. But it's kind of unethical to give them something that is kind of broken in a way that you already understand. So you kind of want to give them the best piece of software that you can possibly give them. So what if, instead of using kind of SOAP-based services, what if we use a REST approach and JSON instead of XML? So what REST is an architectural style. It's not necessarily a protocol. And so SOAP itself is a protocol. And so what you could potentially do is you could use XML in a REST context. And what that means is I would just be using XML as a language effectively, or a data format, and I would still be working with stateless web services. That's the whole point of REST. However, why would you do that? Because we know that JSON is way smaller, it's way easier to zip, and it's way less resource intensive. So typically you use JSON with REST, and it takes way less bandwidth because you're only sending basically attribute and value pairs instead of all of this text around what the attribute names are and stuff like that. So we have a situation where the previous kind of stateful services implementation was okay for people that were in the office using a high-speed internet. It was not great for people who were in the field that potentially only have access to 3G or something like that. However, with JSON, potentially we're going to have REST services or stateless services that allow both of these groups of people to do their job in a kind of ideal way. And so we still have a lot of questions, even though we've kind of come to the conclusion that REST is the way to do things, not necessarily just with stateful services. So we have questions like, what happens if there's no internet at all? Where is the database supposed to be hosted? Is it on premises or is it in the cloud? And what happens if there's a future requirement for phone telemetry? So if we are based solely on the browser itself, you're going to have limited capacity to understand where the user was when they were performing their job and that kind of thing. So there are always going to be questions that come up even after you've answered some sort of core design questions that make you second guess your original answers to those questions. And so this is an example of one of those. Potentially you could go to a meeting and the client would say, oh, well, we need to use the gyroscope of the phone, and then you can't do that if you're sold into a web application that doesn't necessarily have native access to the gyroscope on the phone. So even though we've answered some questions, we still have a lot of questions to go. So exactly like buy versus borrow in terms of libraries. So we've already talked about how you don't necessarily want to hand-roll your own security. You probably want to use security that's already been implemented by someone else. There's also a scenario where you have to figure out if you're going to buy or borrow infrastructure. And so this has become a huge hot button item as things like AWS and things like Azure have become extremely popular ways of getting away with not having your own sort of dedicated SQL servers and dedicated web servers and things like that. So for something like web application, you need to understand if the client wants to host the web application themselves, or if they want to go to a cloud provider like AWS or like Azure and have Azure or AWS host the application. And basically the difference is going to be paying one time for buying a server versus paying month over month for hosting and that kind of thing. So if you're looking at on-premises hosting, a lot of really large clients will fight tooth and nail for on-premise because they will have very large sort of investments in personnel. So they'll have people who are very, very good at security. They'll have people that are very, very good at fault tolerance. They'll already have servers. They'll have dedicated server rooms. They'll have dedicated network topology that they don't necessarily want to duplicatively pay for if they're having some services hosted and some services on premises. The pros of this are that you obviously have total control. You own the hardware, you own the software, and you own everything in between. So if you have the resources to do it, it certainly gives you all that you could possibly imagine. The cons are that you also have total liability here. So if you have a lot of infrastructure, but you don't have a lot of the know-how, so you don't have a person on premises that can manage really tight-knit security, potentially you're going to have a security issue, and because you are on premises, you have nobody backing you up in terms of security. So you're at your own whim to do whatever you need to do. For cloud hosting, this is basically a form of borrowing whole infrastructure. And so you can not only borrow the infrastructure itself, but you can also borrow the people. So there are people that work at Azure and make sure that the servers are responding and make sure that there's fault tolerance and backups and all that kind of stuff that adhere to best practices. And so if you use cloud hosting, there are a lot of pros. The pros are that you get all these massive company security resources, you get their scalability, you get their fault tolerance, and you don't necessarily have to reinvent the wheel on those 3 points yourself. The cons are that you have to pay month to month for each of these things. So if you are utilizing tons and tons and tons of resources month over month, these kind of hosting situations can become much more expensive than hosting your own server. But like I said, it has to be a very large application using a lot of data and using a lot of these sort of core functionality feature sets of fault tolerance or something like that to kind of cost more than buying your own server. It could happen. So this is a great example of a decision that is both deeply technical and completely in the business team's domain. So ultimately, the business team has the wallet that you're taking money out of, and it's the architect's job to present a list of very fine-grained pros and cons for each option, and then try to help them understand what the best fit is for this specific project. And so this is another place to bring up that software architects themselves, the best ones, are also extremely personable, and they're able to have these like kind of chats with a client and take something that's extremely technical like cloud hosting and make it personable enough that the person on the business team that potentially has no idea what the cloud even is can make a decision and feel confident about the decision. So ultimately, it's not the software engineer's decision to make almost in any case. It's ultimately the client's, because the client is paying for it, and it's the job of the software team to kind of help them make a decision that fits their needs. So the next huge limitation that we have to deal with in terms of mobile or web applications that don't have access to the internet is that you can't actually use the application to begin with. So if you're in a situation where your entire company uses a web application and the internet to your building goes out, you are dead in the water. You can't actually get any work done. So on-premise applications will still work largely because you will have connectivity within your office building, but there could potentially be a significant work stoppage if you're using third-party APIs or something like that you have to use the internet to access. So if you have an on-premises database and you have an on-premise web server, you can minimize work stoppage, but you can't necessarily completely mitigate any risk of work stoppage. So what can we do about internet loss and supporting offline mode for web applications? So if you have been through Computer Organization 1 and Computer Organization 2, you have undoubtedly heard of L1 and L2 caches. And applications can also have software level caches that exhibit the same kind of behavior as those caches do, and they exploit the same kind of ideas. So they can improve spatial locality by putting data that would otherwise be in the database on the local machine. So you can think about caching things in browser cookies or caching things in local files or temp internet files. And if you have data in a temp internet file that you can access on the local machine, it is going to be easier to get that information than going across the internet to the hosted database and getting the information from the database. And so A, it's going to be faster, and B, if you don't have internet connectivity, you're still going to be able to access the local cache on the machine. So caches originally really came to prominence when you had web services that were not particularly performant themselves. So when you had things like stateful web services that used the SOAP protocol that require XML, you could wait for a very long time for CRUD operations to complete. And so you might use caches to operate on information that hadn't necessarily persisted to the database yet, and then have retries that would constantly retry to the database to make sure that there is synchronized access from the cache and from the database. You also have these things for areas where you have really low bandwidth, so you could still have web access in a specific area, but you could potentially have a bottleneck between you and the database, and so it might take a very long time, even for REST services to complete their operations, but a cache will make it easier for the user to sort of continue on about their job and not necessarily be married to the data coming back immediately from the service. You could also have really high security requirements in that you don't necessarily want data to go back and forth from machines. You want data to exist only on a local machine and only go across the wire to a database or to another machine when absolutely necessary, because there's always possibility of man-in-the-middle attacks and things like that. So caches will also help in those situations. You have effectively a local database that allows you to do things without going across the internet into the DMZ and kind of maybe exposing data. So if you remember in Computer Organization 1 or 2, you have this kind of relationship where if you have a large cache, that means that you're going to have more likelihood of having data locally, and you have less likelihood of having to go off the machine to get data that you need, and so you'll have a faster application. But what it also means is it's much more likely that you can perform more business off of the internet. So if you have a huge cache that has access to everything in the database, you potentially don't even need access to the internet unless you are synchronizing local data with deep persisted data on a server somewhere. So the larger the cache gets, the more business processes you can support offline. And so depending on the type of application you're trying to build, these caches can become an integral part of actually just having a system that functions and fits all of the functional requirements. So we've talked a little bit about thick clients, and as you might have experienced, you can have some web applications on something like Chrome, and you can have pretty horrible memory management in Chrome, and you can have situations where an application just kind of locks up, or it makes your entire computer run slow because that one tab is taking a whole bunch of memory. And the idea of thick clients is kind of going away, largely because trying to manage session state from a local machine back to a database is honestly kind of hard. So you could have multiple people accessing the same records, and if those records are stored in different remote locations and they are different, it's really hard to programmatically understand which one is the correct one when you go to persist those things to the database. And so using a browser-based application with a lot of caching can give you access to data offline, but it can also make your life really, really complicated. So it isn't necessarily a thing you want to do for every application. You need to make sure that the use cases require access offline. So the entire point of a thick client is that thick clients are basically desktop applications that access information as if they were a browser, but they have way more client-side logic. So a console application with a UI on top of it can be a thick client. A thick client could be a WPF application, it could be a Java Swing application, it could be whatever you can imagine. The idea is that the more business logic, the more local data are required or are used by the client, the thicker and the thicker and the thicker they get. So if you have a very simple browser web application that doesn't have caching, that doesn't have client-side business logic, that's a very thin application. If you have one that has access to all of the database records and a local copy of the database, that's an extremely thick client. And so one of the things that you have to kind of negotiate through the process of design is understanding how thick the client needs to be. How much information do you need in cache? Do you need a cache at all? What kind of synchronization do you need to do? That kind of stuff. So if we wanted to shoehorn caching into our overall diagram here, what we would have is we have a user, they have desktop application, and what we are going to have is a database that serves as a cache somewhere in this diagram. So a thin client is going to basically just use native access to the browser, while thick clients are going to use a whole bunch of file system stuff on the client machine. They're going to use maybe local databases and whatever. Thick clients are going to have a lot of functionality in terms of what they can do offline, but you're going to have to pay for it. So you run into situations where some applications require a thick client access, and a lot of them do not. And when they don't, you don't want to kind of use a thick client at all. If you're doing development in a kind of modern, fully baked framework, something like Xamarin, for example. Xamarin comes with the concept of a client-side cache automatically baked into it. And so it makes it very, very easy to manage. And so Xamarin actually gives you a way of storing stuff natively on a phone without setting up your own database and your own file system access and all that kind of stuff. So a thick client with a cache is going to look something like this. So we have the desktop application, we have a cache between the application and the web services, and basically what's going to happen is a user is going to be completely unaware that this whole side over here exists. So they're going to talk to the cache, and it's going to be extremely quick access, and then behind the scenes, the cache is going to synchronize with the database. So you're going to be able to perform all the business logic that you need. You're going to be able to do all of the data management, but you're working on a local copy, and that local copy is being synchronized with the deep copy as you're trying to do your work. So the happy path is you're constantly accessing the cache, you're never leaving your machine, and then if you have to leave the machine, you're going off to a database somewhere, and after you're done with the process, the data is going to be promoted back from the database to your local cache so that you can go back to the happy path and stay on your local machine. So the problems with solver caching are numerous. And this is kind of the reason you don't necessarily want to default to always having caching. So if you remember from computer organization, you have tons and tons of issues around synchronization. So how do you know when all of the data in your cache is so old that you should just throw it away and then rebuild the cache from the database? How do you efficiently synchronize data? So is it on a timer, or do you synchronize to the database every time somebody updates a record or something like that? How do you synchronize across users? So if two users are trying to access the same record, how do you make sure that they are seeing the latest updates? And how do you know which update is the correct one to apply in which order? And what happens if all of that fails? What happens if in the middle of synchronization the process fails? How do you get back to the clean version of the database in order to proceed to update the database in the correct way? So one of the biggest issues with thick clients and people sort of going away from kind of desktop applications to thick clients that look and feel like web applications was that they needed a whole bunch of resources on each individual person's machine. That isn't necessarily a great situation. And so you need better system requirements to run thick clients. Virtualization can make that an easier experience, so you can use something like Citrix to mitigate the need for really high-powered machines by having a Citrix server that then just sort of delegates resources to an individual user. And these kind of frameworks have been around for forever. And if you've seen a lot of the news coverage around Citrix, around VMware, and how their stock prices have surged after the COVID-19 situation, that is because a lot of organizations still use virtualization, even though web applications themselves have become very, very close to the fully featured kind of thick client experience that you would otherwise get through something like virtualization. So what this is trying to say here is that if you have a thick client, you can bet that that thick client is going to have a lot of system resource needs, and the thicker the client, the more those needs are. If it gets to the point that you have 500 users and each of those 500 users need 32 gigs of RAM in order to run the desktop application, you're going to have a really hard time maintaining all of those machines. So instead, what you can do is you can run the application on a Citrix server, and the Citrix server can serve the application to a virtualized dummy desktop, and then you don't really have the system requirements issues. The problem is if you are using a hosted virtualization service, you're back to your original problem where you can't access the virtualized server if you don't have internet connectivity. So that becomes an additional buy versus borrow question. Do you buy your own virtualization hardware, or do you use a cloud-based one? That's kind of a difficult thing to go through. So that's, again, a question you would have to ask the client and kind of work through based on the specific needs of the project. So through this one kind of example, what we've been able to do is look at the really high-level examples, the different options that you have in terms of architectural designs. We could look at a desktop application, or we could look at a mobile application. We had kind of thought that these won't necessarily work for a number of reasons. We can use a web application. It's a really big term. There are some that are thin, there are some that are thick, there are some that allow you to work offline, there are some that don't. So this is a huge umbrella of different types of applications, and some of those things will work for this case, some of them won't, depending on how the client comes back with some of the answers to questions. So even though we know a web application is better than these other two applications, you still have to ask a lot of questions and do a lot of design work around what the application actually needs to look like in order to make sure that it can support the case that you're trying to build toward. And so basically what you need to do is recognize very early on that in software engineering and software architecture, there's really no one-size-fits-all solution for any sort of project. And so your job as a software architect in particular, or as a member of a software team, is to take a look at the worst possible things that could happen if you take a certain step, if you go in a certain direction, and then try to steer clients away from those worst case scenarios by doing things like proposing caches if they need offline access, or proposing hosted solutions if you feel like they don't have the on-premise resources that they need in order to have an on-premises solution. And the kind of final thing that you need to think about is ultimately the client has the final say in almost all of these decisions, because you're not going to be the ones paying month over month for hosting fees. They are, and they need to be positioned in such a way that they understand what risks they're taking on and what expenses they're taking on by continuing with the project in whatever way you've proposed. So they're not going to understand the difference between a thick and a thin client. They're not going to understand necessarily hosted versus on-premises. So as a software architect, it's your job to kind of contextualize all that stuff in a way that the business team can understand, and make it to where they can make operational decisions that make sense to them. So you can frame it in terms of if you choose A versus B, it will be more expensive by XYZ number of dollars, or you have more risk of security violations or whatever, and then the client themselves can take all the business information that they have and make the decision that's the best for them. And so that is kind of the whole wide world of design. We kind of sped through that. But I wanted to give you a kind of high-level overview of the types of questions that might come up when you're trying to design a system for a specific problem. And so after this, what we're going to talk about next week is implementation. So how do we take all of the answers to questions that we've posed in this lecture and actually make those things into code. And so we're going to talk about some design patterns that you can use for actual implementation, and we're going to talk about how to build software that from the very beginning is easier to test for that next step, which is testing. So thank you very much for tuning in, and please let me know if you have any questions, comments, concerns, and I'm happy to answer those via email or during the weekly meeting. Thanks very much, and I'll see you next time.